is Sarah Malik. I am in the MAA Committee for Undergraduate Students. I'm also a professor at Hood College, and it is my great pleasure to welcome you all here today, as well as to introduce our speaker, Dr. Kevin Knudson. Kevin Knudson is a professor of mathematics at the University of Florida, where he currently serves as chair of the Department of Mathematics. An algebraic topologist by training, his current research interests lie in the field of topological data analysis with a particular focus on discrete Morse theory. Knudson serves on the editorial board of Math Horizons and produces, with freelance writer Evelyn Lamb, the My Favorite Theorem podcast. In his spare time, he enjoys cooking, kayaking, yoga, and playing the guitar. Poorly, but hey, he didn't take it up until his mid-40s. Would everyone please help me welcome Kevin Knudson.
Thanks, Sarah. Can everybody hear me okay? I always wonder with lapel mics, right? It's always this funny thing. So today, we're going to talk about the Platonic solids. Now, the students, how many of you know what the Platonic solids are? A few of you? Okay, good. The faculty, okay, good. All right. So I've drawn them for you. There's 5 of them. There they are. That's it, okay? And I'm going to tell you about them, and we're going to make origami models of 3 of them, and I'll show you how to do the other 2, okay? And they're in, this is the order of degree of difficulty. And the last couple, well, you'll see why we can't do them right now, okay? But that's your homework assignment, okay? So I'll tell you what these things are. I will tell you that there are 5 of them: the tetrahedron, the cube, the octahedron, the dodecahedron, and the icosahedron. Then I'm going to tell you about Euler's formula, and we're going to use Euler's formula to show that these are the only 5. Okay? Because you might ask, why aren't there more? I mean, what is a Platonic solid? It's a regular polyhedron, okay? So what's a polyhedron? You take shapes and you glue them together along their edges so that the vertices and edges line up okay, and then you make it closed, okay? So a Platonic solid is a regular polyhedron. So you use the same polygon. You use, and around each vertex, the same number appears, right? So like a pyramid is not regular, right? Because, I mean, you think about the great pyramids in Egypt, right? They have 4 triangular sides and a square bottom, so you use 2 different kinds of polygons. That's no good, okay? We want to use the same polygon and arrange it in such a way that you always have the same number coming together at one vertex, okay? That's what these things are. And so you might think there's tons of these things. How do you know there aren't so many? Well, Euclid, other EU mathematician, Euclid proved in the Elements, book 13 of the Elements, it's kind of the end, it's the culminating thing in Euclid's Elements, that there are exactly 5 of these things: the tetrahedron, the cube, the octahedron, the dodecahedron, and the icosahedron, okay? That's it. So if you're still coming in, there are materials. You might have to come up front. And by the way, there is no significance to the color of the cards, okay? Don't think there is no significance to the colors of the cards. So don't be alarmed. Okay. All right. So let's start. Let's figure out how to do the tetrahedron. Okay. So I made all these in my hotel room the other day. So this is the tetrahedron. Okay. It is made of 4 triangles. Okay. And around any vertex there are 3 triangles. Okay. Now, for every one of these things, I'm going to have this little cryptic business over here on the right. So V, for one of these objects, V is the number of vertices. So for the tetrahedron, there's the 4 corners. There's 4 of those. E is the number of edges. The edges join vertices together. There's 6 edges on a tetrahedron. And then F is the number of polygons that you're using. So here there's 4 triangles. And then I have this weird formula, V minus E plus F. We'll talk about that later, okay? But here you get 4 minus 6 plus 4 is 2, all right? Let's make one of these. All right, so you're going to need 2 of those business cards. And again, the colors don't matter, okay? And you're going to make a left-handed unit and a right-handed unit. I've got a video I'll show you here in a second, okay? But this is the diagram. And by the way, the little handout in front of you has the same diagram on the front page, okay? So you've got a left-handed unit. What you do is you take a business card and you take the lower right corner, I do it this way, lower right corner, and fold it up to the top left corner. And I'll show you a video here in a second. And when you do that, why is my pointer not working? When you do that, here, bring those two corners together, you'll see you now have two right triangles. There's one there and there's one up here. You fold those over the edges of the card, okay? You do a left-handed one and a right-handed one. So let's roll the video here and see what happens. So see, I took the right corner up to the left, crease it pretty hard, and now you've got these two triangles. You want to fold them over. Okay, so this is the left-handed unit. Now, when you have one of each, I'll show the right-handed unit's coming. Okay, when you have one of each, so you unfold them, you take it apart. You see you've got two what appear to be equilateral triangles. Okay, here comes the right-handed unit. They will fit together in an interesting way. So this video is only about a minute long. Once you do enough of these, you get a lot faster too, by the way. Okay, so now you take your left-handed unit and your right-handed unit. And what you can see is sort of the bottom edge of this one card here, where my thumb is pointing, fits inside of that little groove that you just made. Okay? And once you do that, now just sort of push everything together and keep all the flaps on the outside. One of the flaps will want to go in, but sometimes you just pull it out and there it is. You see? Now, at this point, I have to say, if you're finding this difficult, like if your brain and your hands won't go together, do not be alarmed, okay? This is very common. Every time I do this with students or with any group of people, there's always a significant portion of the people in the room who are very intelligent and understand the mathematics and see it all together and find this really challenging kind of physically. So it has nothing to do with your ability in mathematics, whether or not you can get these two business cards to go together to make a tetrahedron, okay? All right. Everybody got a tetrahedron? Yeah, it's sort of magic when it comes together. Everybody got one? I can I can replay it, sure. Where's my cursor? All right, I'm going to skip ahead because I think you know how to make the units, okay? That's the first unit. Here comes the second unit. All right, and now you'll see how they go together. You don't need any tape. The flaps go on the outside. Ah, see? Okay.
Oh, I put the flaps in the
No, so you put that in like that.
Yeah.
And now you do this. The flaps, keep the flaps on the outside, and then it'll stay. Okay? So see how the flaps are on the outside? Oh yeah, the flaps on the outside. Now it stays together. So like I said, this is degree of difficulty. This is the easy one. Okay? Yeah, talk amongst yourselves. Someone at your table has it. If you don't have it, talk to your neighbor. Well, I was trying to save paper. I'm with you. I can't read it either. What? Yep. Yep. It is nice. Okay, are we good? Everybody's got a tetrahedron? All right, let's make a cube. Yes, let's make a cube. All right. So the cube is the next Platonic solid. This is the one you've known since you were old enough to play with blocks, right? It's just it's a cube. Now, so what's a cube? It's made out of squares. Okay. It's 6 squares, and 3 meet at each vertex. Okay. And again, let's look at this weird formula. So there are 8 vertices. There's 8 corners on a cube. There are 12 edges, if you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And there are 6 squares, 6 square faces. And so V minus E plus F is 8 minus 12 plus 6 is 2. I see a pattern developing here, okay? All right, now, how do you make this with business cards? So now, you need 6 cards. 6 cards. 1 for each face, okay? So what you do is you take 2 cards, you cross them. So like in the middle there, you take 2 squares, you take 2 cards, you cross them together, and don't worry about making it so that the flaps hanging off are exactly the same. They just need to be roughly equal, okay? And then you just fold the flaps over in both directions, and when you take it apart, what you've got now is 2 squares with a couple of bent pieces. Okay, I've got a video for this too. Okay? So let me, and again, the diagram's also in your handout there. All right. So here's this video. Sorry. Okay. So here I'm going to show you how to make these 2 units. So I cross the cards, and then you fold against the edges like that. You need 3 sets of those. Okay, so I'm cheating in the video. I already folded the other 4 cards. Okay, so I showed you how to fold the 2. Okay, and now what do? You take one edge of the square and you lay it inside of a flap like that, and then inside of a flap, and then here comes this. This takes more coordination. Okay, then inside another flap. So you always want the flaps go on the outside, always. Okay. Yeah, I'll play it again. Okay. You need 6 cards. Yep. Then here comes, you see I get clumsier at the end because I'm having to hold 5 cards. And when you're done, you got these 5 cards. The last one's actually pretty easy. Pry up the 2 flaps a little bit. We're going to make 3 of them. That last card goes in. You put a flap over it. And magic, you have a cube. Okay? All right, I'll play it again. Because it does take time to fold units. Okay, make the cross, fold the flaps over. Okay. Then once you have all 6, oh, you're smart. Okay, so now once you have 6 of these, see how you make them sort of perpendicular to each other. You put one in there, and you take an edge, and then the flaps stay on the outside. And the flaps stay on the outside. Okay, looks good. What's up? I bought those. That size, yeah, yeah. Actually, I probably even have like a coupon code if you're really interested in it. But I can show you the box of stuff. Yeah, you can get them at Amazon. Yeah. Okay. Yeah, you will. All right. Everybody got cubes? Is it coming along okay? Again, it's a little weird holding all those cards together. My hands are big enough that I can tend to hold them together, but yeah, all the flaps on the outside. Now, someone up here, one intelligent student already figured out that you can actually hook these things together, right? you've got these flaps on the outside, and you can see that if you took two of them, you could stick them together, you could interweave those flaps. This is a very stable thing. You can play catch with this all day. It's not going to come apart. Are you getting them together? There you go. Yep, okay. May I borrow yours for a second once it's done? Okay. Cool. All right. So, see how they go together? If you interlock the flaps. So if you want to get together with the people at your table and make something big, that's cool. Okay, you can build all, you're making your own Lego kit, essentially, where everything's a cube. Okay? The tetrahedron will also go together, but they won't hold quite as well. Yes? Okay, sure. Let me help you here. Okay, so you got 6 cards. Whoop, sorry. Okay, so here's what you do. See how that goes like that? Okay, and now I just want to put another one, just like that. I rotate it a little, and I put it just like that. Okay, and then do another one. My hands are kind of big. Yours might not be big enough, but put another one against that, all right? Flaps on the outside. And then the last one isn't so bad, all right? Where's your last card? There it is. Can you put that in there? Other way, rotate it. Rotate, okay, the flaps should go down and rotate it 90 degrees. There you go. Right, so put it against that one. And we lost that one. If somebody's not using them, yeah, go ahead. Yeah. Okay, and that one went inside, but there you go. And you can tighten it back up, okay? All right. Okay, we okay with the cubes? Things keep getting more difficult. Are we okay with the cubes? All right, so just for some bonus content, so like I said, these things hook together. Okay, so if you and several of your friends can find 48,000 business cards, you can make this. This is a level 3 Menger sponge. That's me right there, about 12 years younger, without glasses. This woman right here now, Julia Glum is her name. She writes for Money Magazine. It's interesting to see your students go on and do really cool things. Yes? It is exactly 48,000 cards. So here's how you build this. I'll go ahead and tell you how you build this, okay? So what's a Menger sponge? You start with a cube, and you drill out the center in all 3 directions, okay? And then from the remaining 8, sort of if you look at the side, you see 8 squares, you drill the centers out of all of those, okay? If you do this forever, you end up with an object that has 0 volume and infinite surface area, okay? Now, of course, you can't do that in real life. This is an approximation. So we can't drill out. It's easier for us to build up, okay? So if you take 20 of these cubes and hook them together in sort of a wireframe, like a small version of that, that's a level 1 Menger sponge. It's a first level approximation. That's like if you took a cube and you drilled the holes out in the middle, okay? All right, so here's what we did. Everybody in the class, so how many cards is that? So it's 20 of these, so that's 6 times 20 is 120, okay? Now, you build 20 of those and hook them together in the same way, okay? So that's 20 times 120, which is what? 2,400, okay? So everybody in the class built one of those level 2s with 2,400 business cards. Once you get good at this, once it becomes mechanical. You can do it while you're watching TV. Okay? It's just something, it's like knitting or, whatever your favorite, hobby that you can do without thinking too hard about it. Okay? And then we took those 20 that we had built, that each of the people in the class had built, and hooked it together into this gadget. I built that wooden platform on the bottom with wheels so that we could move it around the library. It's not there anymore, but the librarians got tired of dusting it, and so what do we do with it? Well, we just threw it away. I wanted to burn it. Like, I wanted to take it out onto the quad and set it on fire, but the fire department would not give us a permit. Okay? So this is what you can do with business cards. That thing weighs about 150 pounds because it's 48,000 business cards. That's a lot. Okay? All right. The octahedron.
So is that 20 20s or is that more than 20 20s?
So it's
Is that exactly 20 20s?
so take 20 of these, you get one of those, right? The 20 of those and then 20 of those.
And now is that size?
Yes, that's right. Yeah, so it's about 4.5 feet on a side. Yeah, yeah. Okay. Now the octahedron. So the octahedron, we're back to triangles. Okay. It is 8 triangular faces where 4 meet at a vertex. Okay. It's like 2 pyramids stacked on top of each other. Okay. All right, so what do you need here? So you need 8 triangles. We know how to fold triangles, right? We have those left-handed units and those right-handed units. Now, so I need 4 cards. What do I need? How many of each type of unit? So we need left-handed units, we need right-handed units. We need 4 total. How many of each? Okay, let's do an experiment. So, okay, all right, how many people think you need 2 of each? How many of you think you need 4 left-handed units? Okay, how many of you think you need 4 right-handed units? A lot of non-committal people in the room. Okay, let's try an experiment. Right, 3 and 1 doesn't seem likely. Okay, all right. So you need 4 business cards. You're going to fold those triangular units, left-handed units, right-handed units. Okay, so if you're in this column here, fold 4 left-handed units. Okay. If you're in this column, fold 2 of each, 2 left-handed, 2 right-handed, and everybody on this side of the room fold 4 right-handed. Okay? Now, putting it together, just fold and I'll talk, okay? Putting it together is a lot like putting together the tetrahedron, but it's slightly trickier because now you've got 4 cards to manage instead of just 2, okay? But it will come together nicely. Start putting it together as if you were doing a tetrahedron, but then, you put the 2 together, now you're going to stick another card in. I can't explain it. And I didn't make a video, sorry. You just kind of have to try it and see what happens. By the way, notice this formula again. There are 6 vertices, right? There are 6 vertices and 12 edges and 8 faces. And 6 minus 12 plus 8 turned out to be 2 again. What did I tell you guys to do? 4 right-handed units? Do whatever. Yeah, do 4 of those. Yeah. Everything going okay? Okay. That's fine. Do whatever you want. That's fine. If you want to do 2 of each, that's cool. I'm just trying to do an experiment here. Got your units, but yeah, put them together. There's no video coming. So, it folds the other way. Yeah, right, yeah. Yeah, so you start like you did with the tetrahedron, with 2, right? No, other way.
Right, this way.
Like that, yeah. Now, so now another one sort of obviously goes there,
Okay.
right? That's how it goes. Here's what it looks like. Okay, so you start like you did with the tetrahedron, but then, so like take, what'd you make, 4 right-handed units? 2 of each? That's cool, it doesn't matter. Okay, all right, so yeah, so remember, the flap's always on the outside, so stick that in there. Other way, this goes in there, okay. Okay, keep your flaps on the outside. That flap should go out there. There's a flap right there. It should stay on the outside. Yep, okay. All right, so now, if you kept going, you get a tetrahedron. You don't want to do that. So now you need another card. Okay, and it will go, right? You can put that edge right there. Actually, maybe this edge. You might need the other unit might, or that direction unit might not work right there, but you can also put one here, right? There you go. Yep. And now the last card should fit in place. Mm-hmm. Yeah. Okay, so now put it together. Nope, there's no video. Nope, just put it together. Yep. Slightly more challenging, yes? So start like you did with the tetrahedron, okay? So like that. Okay. Let's see now, with the tetrahedron you would just fold it up, but this, now you can put another card. Let's see. Maybe, nope. Nope.
This is very hard.
Nope. Try this one. Nope. It will go once I. Did you make 4 right-handed units? Or 2 of each?
I did 4 right.
Okay, that's fine. Okay, so I want to do this. Okay, so now I've got these 3 together. So keep the flaps on the outside. No, that's not going to go. See, even I have trouble sometimes. So,
This is incredibly hard for me.
no, it's okay. See, so right there's 4 triangles, right? So that's okay. All right, so now I just need to. Let's see. No, you're good. So now that, and then the last card will go right there. It doesn't matter. They're equally. Your folds are a little off, so it's there, but it'll work. Yep, you're good.
He used 2 less than 2.
Okay.
But are you allowed to?
Yeah. I told some of you to use 4 rights, and some use 4 lefts. It'll work. Yeah. Does? Mm-hmm. Yeah. Yep. Right. So now.
She did it, I think.
Get your flap on the outside so it'll stay together. That yellow flap. The yellow flap too. Sorry, orange, not the yellow, orange. I wanted to call that yellow because gold. Maybe that's more like it. Cool. All right.
So we weren't sure how to put it together.
Okay, so again, flap's always on the outside. So something like that. Okay. What is this, 2 of each, or did you do 4? You did 4. You 2 of each. Okay. Anyway, once I've got it together, right? That's already half of it.
Oh, that's
Okay.
already half of it.
That's already half, right? And so now,
So that is
if I do that, and then the last one should plunk in there.
already half
Nope.
of it.
Flip it over. Yep.
Interesting.
No, that didn't work either. Wait a
Okay, but
minute.
I can understand.
But yeah, it goes. Yeah. What's that? I got it yesterday. Yeah. Okay. All right, in the interest of time, we have about 15 minutes left. Okay, so the octahedron is more challenging, yes? Okay, but, so the 4 left-handed units, you got it to work, right? And 2 of each, you got it to work. And 4 right-handed units, you got it to work, right? Okay, so it doesn't matter. They look a little different. The pattern of the flaps will look different. Yep. But we don't care about the flaps. The flaps don't matter. The symmetry of it is different. Right. Right. So the way that so that's absolutely correct. So the way the flaps look around a given vertex will be different depending on the numbers of units that you used. But that's fine. It's still the same thing. Now, here's a question for you to think about. Okay? Here's a question for you to think about. Are these actually equilateral triangles? Because in a Platonic solid, that's what in these things we should be having equilateral triangles. Okay? Think about that. I'm not going to answer that for you. Okay? This one is, but this one's different. I'll show you. 10. Yep. Okay. I seem to have lost my clicker. What do I do with that? Okay. Thank you. I knew I'd put it down somewhere. Okay. Yeah. All right, so moving on. The next solid I want to show you is the dodecahedron, okay? This one is significantly different, and we are not going to do this, okay? But I'm going to show you how. And a dodecahedron is made of 12 pentagonal faces. So we have pentagons, okay? You can count. There are 20 vertices, 30 edges, 12 pentagonal faces. V minus E plus F is still 2. Okay, so here, this is where the stack of paper comes in. So you got that stack of white paper that's sort of rectangular. That is A6 size paper, which is incredibly difficult to find in the US without holes punched in it. So I bought a ream of A4, and I cut down into A6, okay? But the proportions you can figure out. Now, this is going to go out to a YouTube video. In that handout, there's a QR code. Okay? The QR code it's in the margin on page 2, I think. The QR code will pop you out to this video on YouTube. Okay? So that QR code will take you to this video. You might, while we're sitting here, want to fold one of these dodecahedral units. Okay? So you notice 12 A6 pieces of paper. This has some jazzy music, but I don't have the sound activated. Okay, so that's what that paper's for. He's going to show you how to fold this unit. Okay, so you take your piece of paper, fold it short end to short end, fold it in half. Okay, and then you unfold it. Now, then you fold it the other way, but you don't make a sharp crease. You just pinch the point in the middle. So I'll pause it right there. Okay, so all he's done, first he folded it short end to short end, and then you make a little pinch, you fold long end to long end and make a little pinch in the middle so you know where the center point is. That's all you're doing. If you want to fold it all the way, it's fine. It sort of messes with the aesthetics of your final piece, but that's all, okay? All right, then you unfold it, and so now you take the bottom left corner into that center point. This is the end result, by the way, okay? Okay, so you take that bottom left corner to the center point, rotate it 180 degrees, do that again. Bottom left corner to the center point. Okay? Now you're going to take that right corner, lower right to the center. You're just folding all four corners in, but you want to do it in a particular order. Okay? So now you've got this sort of situation. And then you fold it back in half along that initial fold that you made. Okay? And for extra structural stability, you tuck those two flaps inside of each other like that. Okay? Now that thing is very stable. So now you got this sort of, this is already sort of a pentagon, but it's not regular. Okay? So you take that top corner there, and you fold it into the center in such a way that that edge is parallel to the bottom. He's pointing this out for you. Okay? And then you do it with the other corner. Okay? So then, as you can see, you've got a pentagon. Question, is it a regular pentagon? I'll let you figure that out, okay? Now, these things actually hook together. You can see he's got three of these things already. These flaps on the edges tuck into the tops of the pentagons, like that. So this really is a good way to do it, is you make three at a time and you hook them together in this way. And now you have four of these three put together, and then you put the four chunks together. Now, if you want to keep folding these units, please do. I'm going to go ahead and talk about something else. But I will say that I did this in my hotel room yesterday. I'm pretty fast. It took me 20 minutes. Okay? So I recognize limitations of time. But this is a good thing for you to do later. Or if the business meeting's still going on, you want to go to that. That's something to do during that. Okay? All right, but the QR code in the handout will take you to this video. Okay, so you can watch it at any time. It's on YouTube. You can watch it at any time, and this is not my video, of course. All right.
The original shape is it a rectangle or a square?
It's a rectangle. Yeah.
So business cards.
Yeah, it's A6 paper. It's a very particular rectangle. Okay. Finally, the last Platonic solid is the icosahedron. This is the MAA's logo, right? The icosahedron. It is made of 20 triangular faces. Okay, I built this in my room. Here's what I'll say about it. It's stable-ish. It's fine. I'm not going to play catch with it all day, but you can move it around. So you need 20 triangles, 2 triangles per business card. That's 10 business cards. You need 5 left-handed, 5 right-handed. Okay? Around each vertex, you've got 5 triangles. So that means around any given vertex, you're going to have 2 left-handed and 1 right-handed, or 2 right-handed and 1 left-handed. I cannot really describe a procedure for this. So that's the finished product on the left. That's an old picture. This is this unit in progress in my hotel room, okay? And if you look closely, what do you see there? Oh, it looks like a piece of tape, okay? I cannot recommend strongly enough that tape is your best friend when you're doing this, okay? When you put a couple of cards together and you've got the flap on the outside, stick it with just a little piece of tape. Now, there is no tape on this structure right now. Once it's together, it will stay together. Once you get that last card in place, it's together. Okay? And you can take all the tape off. Okay? But like I said, I can't describe it. and a video would last too long, and folding the cards takes too much time, etc. This is your take-home assignment, okay? You know, tweet me a picture or whatever when you get it done, okay? It's very cool. It takes a lot of, it's a challenge, but this is your special challenge. Okay. So, again, there are 12 vertices, 30 edges, 20 triangular faces, and so v minus e plus f, again, is 2. All right. So, so was that a coincidence? No, of course not. There are no coincidences in mathematics. Well, sure there are, right? But if you look at all of these, for these 5 solids anyway, we got 2. Now, has anybody been to the exhibit hall and been towards the back and seen that big thing with all the stuff hanging? Okay. And if somebody was up there telling you how to do it, like get down and look up, the tetrahedron's down in the bottom, right? And if you look up at that thing, they all look like they're lying in a plane. And they are. And the plane is, there's a number of vertices, the number of edges, and the number of faces. If you want to think of rectangular coordinates, that's x minus y plus z equals 2. That's a plane, right? So it's kind of weird that all these things lie in a plane, right? That's Euler's formula. So now some people argue about whether or not Euler actually had a good proof for this, but he observed it anyway. And so you have a convex polyhedron. There's a more general result than this, but I'll just say it here this way. You have a convex polyhedron, meaning there's no dips in it, okay? V minus E plus F is always 2. This is a remarkable fact. So David Richardson wrote a book called Euler's Gem. It's about this. It's fantastic. I highly recommend it. Let's prove it. Let's prove it. I'll demonstrate the proof for a cube, but this sort of works in general, okay? Here's the idea behind Euler's formula. In some ways, it's a graph theory question, okay? So you imagine the edges sort of form like a wireframe, okay? And one way to think of this is if you just sort of stretch, you look through one of the faces and kind of stretch the edges of it out so that everything else fits inside of it. Like this is like looking through the top of a cube at the rest of it. That's what it's going to look like, okay? So one way to think of that is the top face of the cube is outside of this square. Or you could imagine, remove one face and now stretch the rest of it out so that it lies on a plane. It's not entirely obvious you can do that, but you can, okay? And now what you do is, okay, so let's think about the fact that maybe I've removed a face. So now I want to show that V minus E plus F for this thing equals 1, right? Because I removed a face, okay? All right, well, here's the idea. Find an edge on the outside. Okay, and remove it and the face that's on the inside adjacent to it. Okay, so I'm going to remove that edge on the right and that square, it doesn't look square, that trapezoid that was next to it. Okay, have I changed the quantity V minus E plus F? I removed one edge and one face. So I haven't changed V minus E plus F, no matter what it is. Okay, do it again. I still haven't changed it. And again, and again. Now I've got these sort of spokes sticking out. Let's remove one of these vertices. I think maybe this is one that's going to disappear. This vertex and this edge, okay? So I removed a vertex and an edge. I did not change V minus E plus F. It's because of the plus on one and the minus on the other, right? Do it again and again and again. Okay, now I've got this. Remove an edge and the interior square. And now I've got these vertex and edge, vertex and edge, vertex and edge. And now I'm down to one vertex. What's V minus E plus F for a vertex? Just what I wanted, okay? This proof is sometimes called letting the ocean in, right? You just sort of start on the outside and you remove edges and faces and edges and faces and edges and faces until you're down to what is a graph that is a tree, and then you remove vertices and edges, vertices and edges, vertices and edges until you're just down to a vertex. That's the proof. So I learned this theorem the first time. I'm a topologist, so of course I like it. There's lots of ways for me to think about this. I learned this theorem in a graph theory course. And the fun part is, so did anybody go to the jam session the other night? Bud Brown, the gentleman, okay. Bud was my linear algebra and graph theory teacher at Virginia Tech. And Bud taught me Euler's theorem. So, okay? Now, how does this help us decide how many Platonic solids there are? Here's one proof. Here comes the algebra. This is not Euclid's proof, right? Euclid, this would have made no sense to Euclid, right? So here's the idea. Suppose you have a convex polyhedron, and all the faces are m-gons, the same polygon, okay? And assume that you have n of them coming together at a vertex. So for example, for a cube, m is 4, because I've got squares, n is 3. 3 of them come together. Okay, so then here are the relations. How many vertices are there? Well, for each face, you have m vertices, but they get counted n times each, right? Because n faces come together at a vertex. So the number of vertices is m times the number of faces, but you have to make sure that you don't count them repeatedly, okay? And similarly, the number of edges is, well, there are m edges for each face, and 2 of them meet. So you're counting them twice, okay? And now you just throw all this into Euler's formula. 2 is v minus e plus f, but I know what v and e are in terms of f. So you get this, and then you solve for f. F turns out to be 4n over 2m minus mn plus 2n, okay? That's just what happens. There are other ways to do this using Euler's formula. This is the way that I decided to do it when I was writing the slides, okay? This is actually ugly. I probably should have done it a different way. If you look at the Wikipedia page, it's cleaner, but I was just doing this off the top of my head. So this is the formula for the number of faces in terms of n, which is the number of things that meet at a vertex, and m, the number of sides on a polygon. Okay? Now, P is convex. So we have m-gons, right? You can't have more than a hexagon. First of all, you have to have at least, so n has to be at least 3, right? You have to have at least 3 things coming together at a vertex, otherwise you wouldn't get a solid, okay? So you got at least 3 things coming together at a vertex. 3 hexagons at a vertex are flat, right? You tile the plane with hexagons. So if you had something more than a hexagon and you have 3 of them, you lose convexity. Now you can make polyhedra that look like that. You can use heptagons and octagons and decagons and all that, but you'll lose convexity. There's no way to do it, okay? So m is at most 6, but then it's also, it can't be more than 6 either. Okay, so it's a case analysis. So m is 3. You have triangles. Then f turns out to be 4n over 6 minus n, but f has to be positive, right? So n is at most 6. So n can be 3, 4, or 5. That is the tetrahedron, octahedron, icosahedron, respectively. Or m is 4, so you're using squares. You get exactly one possibility. 3 meet at a vertex, and that's the cube. Or m is 5, you're doing pentagons. There's exactly one possibility. N equals 3, and f equals 12. That's the dodecahedron. Okay? We've classified. We did what Euclid did. Yay! Okay? Interesting. So Euler's formula is really fascinating. You can deduce all kinds of stuff with it. Here's one of my favorite facts about polyhedra that you get out of Euler's formula. So, definition. A buckyball is a polyhedron made with nothing but hexagons and pentagons. Okay? Nothing but hexagons and pentagons. So a dodecahedron is an example. It's made of hexagons and pentagons. We didn't use any hexagons. Okay? The Women's World Cup is going on. There are lots of buckyballs flying around that field. A soccer ball is a buckyball. Okay? It's made with hexagons and pentagons. How many pentagons are there on a soccer ball? Has anybody ever counted? There are 12. Okay? So, theorem. In any buckyball, there are exactly 12 pentagons. No matter how big it gets, and you can use lots and lots and lots of hexagons, there are only 12 pentagons. Drops out of Euler's formula. It's a fun little exercise. You should think about it. Okay? All right, well, my time is up. I hope you've had a good time. I hope you go home and make your dodecahedra and your icosahedra. Okay? Take these cards with you because I don't want to take them home. Okay? And enjoy the rest of your time at MathFest, okay?